So in the previous videos on pH, we discussed the topic of pH curves. And one thing that pH curves illustrate is an interesting property that some solutions have. All right, we'll get back to how these relate to pH curves in a little bit. But for right now, I want to just introduce the concept of what's called a buffer. All right, so I'm going to compare two different solutions here. One is going to be just 9 milliliters of pure water. All right, and when we have pure water, I think by now we would realize that the pH of it would be 7. All right, so let's pretend that we add a milliliter of 1 molar sodium hydroxide to that. All right, well, that would make it 10 milliliters of total solution, and we could calculate the concentration of the hydroxide, and we could calculate that the pH of that solution would be 13. All right. Alternatively, if we took that same pure water and added a milliliter of 1 molar hydrochloric acid, which is a strong acid, we would get a solution which has the pH of 1. All right. So what this illustrates is that when you take pure water, all right, which is what is considered an unbuffered solution, all right, even the addition of small amounts of strong acids or strong bases can have drastic changes in the pH. All right. And what I want to contrast that to is what would happen if you did the exact same thing to what is considered a buffer solution. All right, so I'm not going to mention right now what is actually in the solution. We're just going to call it 9 milliliters of a buffer solution, which is at pH 7. All right, so notice we're going to do the exact same thing. All right, we've got the same volumes of the original solution, and we're going to add the same amount of the 1 molar sodium hydroxide. And notice what happens here to the pH. All right, when this is pure water, you get a huge change in the pH. But when it's a buffered solution, you only get a very, very tiny change in the pH. All right, in fact, it barely changes at all. All right. On the other side of things, if we add the 1 molar HCl, we would get only a very small drop in the pH. All right. So let's take a look at what's going on here. So what we have here is a solution that seems to have a resistance to having its pH changed. All right. So the name of such a solution that has this property of wanting to resist having its pH changed is called a buffer. Okay. So let's take a look at why buffers have this particular property. All right. So first of all, what is a buffer? All right. A buffer is going to be a solution that contains significant amounts, all right, ideally 50-50 ratio, but it doesn't necessarily have to be exactly 50-50. You just have to have significant amounts of both the acid form of a weak acid, HA, and its conjugate base, A-. All right, so you want a solution that within that solution you're going to have about roughly 50% HA and 50% A-. All right. And so let's take a look at why does having that in a solution create a solution that is very resistant to having its pH changed. All right, and to start this, let's recall what it means to be pH. All right, remember that pH, mathematically it's the negative logarithm of the hydronium or the H3O plus concentration, but effectively it has to do with the relative concentrations of either H3O plus or OH minus. The charges, by the way, should be inside of the square brackets. That's a typo. So remember, if you don't change the relative amounts of this, you don't change the pH. All right. If you do change the relative concentrations of these things, you do change the pH. All right. So with that in mind, let's go through this just graphically. All right. So first, let's think about why is it that when you add strong acid or base to pure water, why does it cause the pH to change? All right. So this right here is just a representation of what pure H2O, which we could consider an unbuffered solution. All right. So to represent this, I'm just going to show up a couple of H2O molecules. And let's think about what all is in there. All right, so first of all, we have a lot of water molecules. And this is an exaggeration, all right? So what else would be in there? All right, we are going to have some hydroxide and we're going to have some H3O+. All right, so where do these come from? All right, the hydroxide and the H3O+, those come from the self-ionization of water reaction. All right, so recall you're going to have literally billions of water molecules, but every once in a while you have that you're going to have a hydroxide ion, and you're going to have an H3O+ from whenever two water molecules get together, and one temporarily gives its H+ to its neighbor. All right. So even though I'm representing it showing 3 water molecules, 1 hydroxide, and H3O+, please remember you literally have billions of these for every one of these and every one of these. All right. But the presence of these is very important. All right. When you're measuring the pH, it's the relative amounts of these guys right here, which is the difference between a pH of 1 versus a pH of 13, for example. All right. So let's consider the situation if we were to add some hydroxide to pure water. All right. So if we add some hydroxide, say if you added some sodium hydroxide to this right here, what would happen? All right. Well, don't think too hard about this. You're just going to add an extra OH minus. All right. So what would you have in the resulting solution? All right. Well, down here you can see we have exactly the same thing that we had before. And we've just, this right here, that's just one more added OH minus that we didn't have before that we got because we added a little bit of the sodium hydroxide. All right. So recall, what changes the pH? It's going to change if the relative amounts of H3O or OH minus changes. All right. And notice we have changed the amount of one of those. We now have more hydroxide in the solution than we did before. All right, so the added hydroxide increases the concentration of OH minus, and therefore that causes an increase in the pH. All right, let's consider the other situation. Let's add some strong acid. You're essentially adding H3O+, and if we do that, well, this is what you have originally, and so you're going to have that original solution plus some extra H3O+. All right, so the added H3O+ increases the concentration of hydronium ion, and that's going to cause the pH to drop. All right, so let's contrast that to what happens if you have a buffered solution. All right, so what are you going to have if you have a buffered solution? All right, essentially a buffered solution is going to be exactly like what you would have with water. Okay, so we got billions of these water molecules. We have an occasional hydroxide, which would be matched by an occasional H3O+. But the one thing that's going to be different that you're going to also have in a buffered solution is, as we mentioned, you're going to have a 50-50 ratio of of a weak acid and its conjugate base. So we're also going to have, we're going to say one of these and one of these. All right, that's a 1-to-1 ratio between those guys. All right. So how does that, affect things when we add strong acid or base? All right. Well, notice that when we did not have those, any added hydroxide to the pure water ended up in increasing the number of hydroxide ions that were in the solution. All right. We've got one extra hydroxide here versus before. All right. But the thing is, what's going to happen if we add hydroxide to this buffered solution? All right. Well, the thing is, we now have something that can react with that hydroxide. All right. And one way to put it is to say that there's something in there that can absorb this added hydroxide. And that's because when HA reacts with OH minus, this is a weak acid and this is a strong base. This thing's just going to give its H plus to that base. All right. So this, and I drew the arrow here so that you could follow the exact reaction. If you added this guy, it would give an H plus to the OH minus. That would make a water molecule. So you now have one extra water molecule. And then what's left over? You've got an A minus. All right, that's what's going to be left over after this HA gives away its H plus. All right, so let's take a look at what's now in the solution. All right, Well, the only difference between what we had before and what we have now is that we no longer have an HA in there. All right, we have an extra H2O, which isn't going to really affect much, and we have an extra we have an extra A minus. But notice what didn't change. We don't have any extra OH minus. We don't have any extra H3O plus. All right, so by comparison, before, added OH minus resulted in an increased amount of OH minus in the solution. Here, added OH minus has no effect on that. All right, and that's because the OH minus gets absorbed, reacts with an HA, so that it doesn't result in an extra hydroxide being there. All right, so by contrast, what's going to happen if we add H3O plus? Well, recall that we've got 50-50 of these guys in here. And if we add H3O plus, the thing that's going to absorb that is this A minus right here. So if H3O plus gives an H plus to A minus, that's going to result in this reaction right here, this second line. All right, that's going to give an extra HA. So H3O plus gives an H plus to HA. That creates this HA right here. It also creates a water molecule when this guy right here loses an H plus. All right. So notice what happens here. All right. We added an H3O plus, but we don't have any extra H3O plus in solution. All right. So and the reason for that is the H3O plus gets absorbed by the A minus. All right. So long story short, the HA and the A minus, the HA would absorb any added hydroxide. The A minus would absorb any added H3O plus. All right, but the ratios of the OH minus and the H3O plus don't change. All right, and I do want to point out that this is a little bit of an oversimplification. Notice that when you add the strong base, you do get a slight increase in the pH. You know, with strong acid, you do get a slight drop in the pH, but nothing compared to what you have if you added it to an unbuffered solution.